welcome to the next lecture in the Shulman lecture series associated with the Physics of Dance class. The Shulman lectures are presented under the auspices of the Franke program in the Sciences and the Humanities. It's made possible by the generosity of Richard and Barbara Franke, and the series is named after Robert Shulman, right here, who is the Sterling Professor Emeritus of Chemistry, Molecular Biophysics, and Biochemistry, and Senior Research Scientist in Diagnostic Radiology, in recognition of his roles as a founding fellow of the Whitney and as an unwavering supporter of the integration of science and the humanities. Tonight, we're honored to have Professor Young-Kee Kim here with us. She is the Lewis Block Professor of Physics at the University of Chicago. And I don't know if I'm buzzing or if somebody else is buzzing, but maybe I'm okay. Okay. So, Young-Kee I have known throughout my entire career in particle physics. She was one of the first people I met when I started working on the experiment. She hosted all the young students in her apartment outside of Fermilab to talk about science and detectors and physics every week as she made us pot stickers that we ate and had conversations. So she was an early mentor for me, so it's wonderful to have her here. She also is extremely distinguished within the field of particle physics. She has served as the spokesperson for the CDF collaboration of 500 members. She then served as the Deputy Director of Fermilab, which is the only high-energy physics dedicated lab in the United States. So it's an extremely important piece for our field. She's most recently been leading initiatives at University of Chicago and also thinking more broadly about accelerator physics and supporting accelerator physics, which is an incredibly important part of our being able to do our science and something that we haven't been thinking about broadly enough as a field. So we're grateful for her leadership there. One of the reasons that we've asked Young-Kee to come and talk to us as a part of this lecture series is that she does have, she has thought quite a bit about intersections between science and art, science and the humanities. So she's on the board of the Gray Arts Center in Chicago. She's also, within the University of Chicago, on the board for the Science, Arts, and Environment Initiatives. And personally, she has a background in dance, and with her husband has hosted salons, art salons at her house for the past 9 years. And she's had, at this point, over 70 salons that they've hosted at her house. We've asked Young-Kee to come here and talk to us about research and the ways of knowing as she sees them in the discipline of physics, and to give us some physics intuition and teach us some things. Our class, Physics of Dance, looks at our two disciplines, physics and dance, and how we gain knowledge in these two disciplines and the interactions between them. We're excited that she'll be joining our course dinner afterward, and we'll explore some of those things a bit more. But we're excited to hear about the ways of knowing and research in physics as she talks about an atom as an onion. And thank you very much, Young-Kee.
Thank you, Sarah. That was a very generous introduction. Maybe I'll stop here. Okay, so I'm very happy to be invited. Is it okay? Is it too loud or too soft? Very pleased to be invited for this outstanding program that Sarah and Emily have been doing. I've been talking to them a little bit, and I really admired what they have been doing. I wish I can do. I'm going to pick some of their brain, and I'll try to implement something in Chicago, and I hope I'll do that in the future, but we'll see. I'll probably have more collaboration with them and probably have help from them if I want to really make that happen. But today's my lecture or the talk is about a journey in searching for the most fundamental unit of a matter. We call them elementary particles, or in his talk I will say building blocks. And to get to or understand the building blocks, we need to peel matter layer by layer, as if we peel an onion layer by layer to see what it is at the core. So I'm using onion as bioanalogy in many slides here. I hope you enjoy. I didn't. So I prepared this talk actually just for this one. So this is my first trial. See how it goes. I may have to policy if I want to use the same thing in the future. So this is a trial. So this is the really understanding the building blocks is the main theme of particle physics. This is a field of science research. And just let me say a little bit more briefly of what we are trying to do. So like what I said earlier, our goal is to understand what the universe is made of and what holds it together. So this first question is about the building blocks, or as I said, elementary particles. And the second question is about how these building blocks interact each other, or forces between them to make all of us, to make the universe. So that's the second question. Again, this is about forces between the building blocks. So I'm pretty sure that human beings, whatever the beginning of human beings, many people have thought what we are. I mean, that's how religion is perhaps created, and partially also the philosophy and all that. We are always wondering who we are and what we are made of, what the world is made of, what the universe is made of. So it's nothing, any particular question about particle physics, but I believe that it has been going on the history of human beings. But the first person, at least to literaturely, who really gave more thought on the building blocks is Democritus about 2,500 years ago as a natural philosopher. So to him, universe is composed of two elements. One is atom, or atoms, and the other is the void in which atoms exist and move. So atom is a Latin word. What it means is something that you cannot destroy or divide it. So by construction or by concept, atom is the building blocks for this Democritus. And from his view, this is indestructible, solid, invisible, and homogeneous, but there are many different kinds of atoms, different sizes, different masses, different shapes also to really explain what we are made of. So for many centuries, atoms were thought to be the most fundamental unit of matter or building blocks. And this concept of this atom, as you know, and I'll say more today, so we know that atoms are not most fundamental particles or building blocks. They are made of something smaller. So their modern physics, modern research already showed many times that there are something smaller than atom. So it has many changes. However, the philosophy of Democritus of the atom remains the foundation of modern science. So this is, again, building block concepts. Yesterday's building blocks may not be today's building blocks, but the concept is there. So let me now jump to 1900, because for many centuries, we didn't really know the inside of atoms. Only around 1900, or a little bit before 1900, people start seeing something inside. So this will be the picture of atom, or at least the concept of atom around 1900. That's soon after J.J. Thomson discovered electrons. So we know, and scientists knew then, that atom is not a fundamental particle, but made of positively charged part and electrons. So the model they had is called the plum pudding model. That means the atom is kind of ball or sphere, but it's very soft tissue-like or sponge-like material, not really solid. And there are electrons all spread out. So this is a kind of a Christmas plum pudding model, is what they thought it would be. So obviously, people want to understand more about atom and what's inside. And we want to peel an atom to see inside. And the Rutherford and his team, and actually he has a brilliant two other researchers working with him, and we discovered what's inside. So let me say a little bit about that. This one is a replica of their instrument in sort of tabletop. Experiment, and just showing here, so inside they have radium source that emits alpha particles. Alpha particles are sort of positively charged with the 2 protons in it. So those particles are emitted from this radioactive material with a relatively large energy. And they fire this beam of alpha particles to a very thin gold foil, shown here. And so these alpha particles go through, most likely to their mind and model that I showed you, zip through this foil and land somewhere there. So they were checking where they really land here or somewhere else. But for their mind, it's just coming there because this is nothing but kind of soft tissue-like material. So again, this is a sort of model they thought of in terms of atom, and alpha particles go through, zip through. So this is their instrumentation here. This is their alpha particle source to a thin gold foil, and that's what they expected. All the alpha particles end up landing here. But then what they've seen is, in fact, that most of them land here. But once in a while, some of the alpha particles have scattered and make angle like that. You may not see very well the screen. So that's very different from their model. But most interestingly, very rare, but some of them, once in a while, this alpha particle hit here and almost bounce back to you. So this is an incredibly surprising result. In fact, Rutherford himself said the following: it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So that much of a big surprise. So they knew from these various experiments they went through that there's a positively charged particle. It's very small and at the center of the atom. And exactly how small that is, they can tell based on how often they see particles bouncing back. And I said it's very, very rare. That means that the size of this core positively charged element is extremely tiny. So this is their view from these experiments. There's an atom, and there are electron clouds orbiting. But inside, at the center, there's the massive, intense charged particle. And the nucleus is another Latin word meaning a small nut. So you can see that there's a very small and very intense, massive element in there. The size, based on their experiments, is about 10,000 times smaller than atoms. So it's extremely, extremely tiny. And almost all the mass, our atom mass, is really concentrated on that because electrons really don't have much mass at all, very, very light material. So you can imagine that's a very, very interesting and unexpected result. So another interesting part is that because the nucleus is such a small element, if you look inside of atom, you can imagine this is a void. Like in the solar system, if you look at it, there's a sun and with Earth and some other planets. But in big picture, there's almost all space is void. So you can see the very interesting similarity between the inner space and the outer space. And there's a word around that time or after comparing the size of the nucleus to the size of atom. They're comparing the fly in the cathedral. So if you think a cathedral as the size of atom, fly in cathedral is the size of atom. So it's quite interesting. Except that the entire cathedral mass and weight goes into the fly. So imagine that. So now question is whether the nucleus is the fundamental unit of matter or building blocks. Well, we have seen that there's something inside the atom. So obviously you cannot stop there. We have to peel another layer to see whether the nucleus is really building blocks or not. So in fact, that 1932, the discovery of the particle called the neutron, that made it much clear that nucleus is not building blocks, but they are made of something smaller. We call them protons and neutrons. Protons are charged particles, and neutrons are neutral particles. So there are a lot of studies following these discoveries of protons and neutrons about the nucleus, what they are and how many protons and neutrons are included in the nucleus and what the properties, what kind of energy levels they are, so on and so forth. There are tremendous study done, and one of the big contributors in this, the study of the nucleus is Maria Goppermeier, who received the Nobel Prize for her outstanding accomplishments. So this is her quote. Protons and neutrons spin along orbits like several shells, much like an onion with many shells. So she had this knowledge of the onion layers and shells with how the protons and neutrons might be orbiting within a nucleus. So she got the nickname, the onion Madonna. I didn't know about that until I prepared this lecture, and I was searching and discovered this one, so that was a pleasure. So what's next then? So clearly nucleus, which is about 10,000 times smaller than atom, as I said, it's made of something smaller particles, protons and neutrons. And indeed, for a couple of decades, people thought that protons and neutrons are building blocks, of course, together with the electrons. But then we cannot stop peeling. So we want to know whether protons and neutrons are building blocks or not. So for that, we need a bit much better, more powerful experiments, power tools, because we have to see something inside. And let me just give you a brief explanation of what we needed to see something inside. So I see you and you see me, we see around here because we are using light, the beam of light to see us. And if you want to see inside of you, we need, for example, X-rays to see inside of us. We cannot see ourselves just using visible light. We cannot see what's going on inside. So we need X-rays, as you know very well. So now if you compare them, the lights have its own wavelength of about a few hundred to probably 800 nanometers. Nanometers is 0.801 meter. So very small, and about the size of atom. And this visible light is probably about 100th times the 100th of your human hair, typically. So that's the wavelength of this X-ray, visible light. And X-ray is about a couple of orders of magnitude, a smaller wavelength. So because of that wavelength is smaller, so we can see something small scale objects and penetrate inside of your body to see that. In other words, they are both electromagnetic radiation, but light has lower energy than X-ray. So if you have a beam of radiations or beam of particles which have a much higher energy, then their own wavelength is smaller so that we can see something very small scale, and that's the concept. So in order to see inside of protons and neutrons, we need a very, very high energy beam of particles. So that's what this shows, that this is any object, if you want to see inside, deep inside, we need a high energy beam of particles. And if you want to see something even inside, deeper, or at smaller scale, then we need a higher energy beam of particles. So accelerators do produce a very high energy beam of particles, and let me say a few words about that. So really modern accelerators were invented in 1930 by Ernest Lawrence. He was then professor at UC Berkeley. So his first invention of the accelerator is about 4-inch diameter. It's the size of your palm, as you can see. In the last 8.5 decades, there are many generations of accelerators starting from there, and one generation to next, built on the experience and the technology, we able to make a better and better accelerators. And here are the most powerful and complex accelerators at the modern days and today's. As you may have learned or know very well, this Large Hadron Collider at CERN in Geneva, that is the biggest accelerator in the world. Its accelerator itself, everything is underground. the length, circumference of this accelerator ring is about 16 miles. So you can imagine compared to what it was to modern days. So there's another accelerator at Fermi National Accelerator Laboratory near Chicago. They have also very powerful accelerators, but they are not the same kinds. They produce a very intense beam of neutrinos. Also, they are planning to make a very intense beam of muons, and these will also be needed to study who we are and what we are made of and how the interactions or forces between them. So not only like a proton and proton collider, that's Large Hadron Collider, we need other kinds of accelerators to do this study. We also have a very powerful accelerator in Japan. They use electron beam and its antiparticle called the positron. We accelerate them and have them collide heads-on. They also have kaon beams and neutrino beams and muon beams, etc. So these are three biggest or the most powerful accelerators for the study of particle physics. So let me just stop one moment and just tell you about building blocks of yesterday and building blocks of today. As I mentioned, for many, many centuries, atoms were thought to be building blocks of everything in the universe. And early 20th century, the discovery of a nucleus, now we know that nucleus and electron, they might be building blocks of the universe. A couple of decades later, seeing peeling the nucleus, scientists discovered that the protons and neutrons are they make a nucleus. So for a couple of decades, they thought proton, neutron, electrons are building blocks. And seeing inside of a proton and neutron with all this technology of accelerators and also the beautiful and wonderful well-performing detectors, we also know that they are not elementary particles or building blocks, but they are made of something smaller. We call them up quarks and down quarks. So that's still the building blocks that we know of, and we haven't seen anything smaller than that. So the current picture is protons and neutrons. They are made of up quarks and down quarks. Proton is 2 up quarks and 1 down quark, and neutron is composed of 1 up quark and 2 down quarks. So here I show helium atom, but if you look at the hydrogen atom, nucleus is nothing but just 1 proton. And there are other the elements or atoms, different kind of atoms. They will have different numbers of neutrons and different number of protons, therefore different number of electrons. But everything is made of up quark and down quark and electron. If you think about it, this is a fascinating story. All the chemical elements, we know they behave very, very different. But if you really go look deep down, they are all made of the same thing, and that's remarkable. So what about the interactions or forces between them? We know that, again, from these experiments using accelerators and so on and so forth, that at the scale of about the nucleus size or even smaller, meaning that any 2 building blocks, they are separated by the scale of distance of a nucleus size or even smaller, the dominant forces are weak forces and strong forces. Weak forces are responsible for radioactive decays, and strong forces are responsible for binding quarks to make protons and neutrons and binding them to make a nucleus. So they are the fundamental 2 forces in 2 over 4 forces in nature. But if you are at the scale of atom size, then these forces are pretty much negligible, and dominant forces are electromagnetic forces. In fact, at the human scale, dominant forces are electromagnetic forces. Of course, if you go much bigger, the gravitational forces also are dominant ones. So there are 4 forces in nature that we know of. So let me just quickly, again, looking at the size, as I mentioned, that the nucleus is about 10,000 times smaller than atom, and they are made of protons and neutrons. And quarks, these up quark and down quark electrons, again, with the modern technology, we're trying to see even deeper and deeper, But at this level, the size up to about 100 million times smaller than atom. Even if we look at that small scale, we find that quarks and electrons are still the building blocks. Whether if we have a better tools in the future and see even smaller, deeper, whether they still end up the building blocks or not, of course you don't know, and only future we can tell us. So you know, you are very familiar with the periodic table of elements. These are all the different kind of atoms, and based on their chemical properties, that means based on number of protons and number of neutrons in the nucleus, you can make a very nice chart of the table. Again, this is a very powerful the table in a sense because it describes very well the properties of these atoms. And I would say that is one of the big accomplishments of the 19th century. But in the 20th century, in the physics side, as I mentioned, the up quark, down quark, electrons are building blocks. Doesn't matter which element you pick, if you look at it, they are made of these three the building blocks. But while we have a powerful tools and to see really peeling all the atoms layer by layer and see deep inside of the atoms. So with the same the technology and same tools, by doing so, we also have some surprises and big discoveries made, something that's very unexpected. I told you and I showed you that we often create very high energy beam of particles from accelerators and fire at a target. Gold foil is one of such a thing, and see what's inside. We also, scientists discovered that instead of firing at a fixed element, if you also accelerate one beam of particle and the other one and have them head-on collisions, then we can use the energy of these beam of particles much more efficiently. So that's why the colliders are invented. Again, very high energy beam of particles and another high energy beam of particles, we just collide them. Then, of course, we'll have a lot of energy available. But then Einstein told us that energy and mass are equivalent. That is, if you have a lot of energy, we may be able to create a very massive particle. Here, this famous equation, E stands for energy, and M stands for mass of the particles, and C stands for the speed of light. So when we have a very high energy, we can make very massive particle based on this equation. These are not ordinary. These are not up quark, down quark electron, but these are much more massive than those. In fact, these are very exotic particles. We don't see them in nature in abundance, but we believe that they were there at the beginning of very early moment of universe, when universe was a very, very hot and high temperature and high energy. We can conclude that because with a very high energy accelerators, we were able to produce them. So with the same concept, with the energy available at the very early moment of universe, we should have such particles existed. So these particles, they are very, very unstable. That's part of the reason why we don't see them in nature in abundance. So they immediately decay with ordinary particles like electrons or protons or pions, things like that. So as a particle experimentalist, we build around, detector around this area, and just look at them, study them. First, we identify who they are. Are they electrons? Are they protons? Are they neutrinos, and etc. And also we measure their charge, we measure their energy, and so on and so forth. From all that measurement of these daughter particles, and we'll be able to see, there's in collision time, this kind of exotic particles might have occurred, and that's how we do an experiment. So this is, when I started my particle physics research late 1980s, this is the picture of all the particles created by the accelerators, by the modern accelerators. So let me go through a little bit on that. So here are this is United States. This building blocks, so elementary particles, meaning that these are all elementary particles. That means they are not made of anything smaller, like up quark, down quark, electron. They are all elementary particles. So I made here that area of this disk is proportional to their mass. So as a comparison, this is how it looks like if we make a disk using hydrogen atom or proton or neutron. That will be how much the mass it is like, and compared to the others. So charm quark and tau lepton, these are new elementary particles, were discovered at the SLAC National Laboratory. Charm quark is also discovered at Brookhaven National Laboratory. And neutrino, one kind of neutrino, there are 3 kinds, muon type neutrino. By the way, this mass is extremely tiny. It's about 1 million times smaller than electrons, so you can imagine how light that is, was discovered at the Brookhaven National Laboratory. Fermilab discovered the bottom quark, which is about 5 times the proton mass or hydrogen atom mass. So these are all, if you study their properties, each one has half unit of spin. And we call them fermions. So I put them as red colors. The other particles, like gluons are mediators of strong forces. Again, I said the quarks, between quarks, there are strong forces, and gluons are carrying the strong force. They have spin, 1 unit spin, and we call them spin 1 boson, and discovered in Germany, a laboratory called the DAISY. And W and Z boson, these are force carriers for weak interactions, and they are discovered at CERN, and they also have a spin 1 unit, bosons, and their mass is about 80 times proton or hydrogen atom mass, and Z boson is about 90 times of that. So these are all spin 1 bosons, so it's kind of interesting to see that one type of particles are discovered in American continent, the other kinds of particles are discovered in Europe. So that's what I studied. Let me quickly go through my experience, at least the projects that I was involved in my career. So that's where I studied in Japan, using Japan, the electron pulsing accelerator. It's about 2 miles of circumference of 2 miles. Then I spent a couple of decades at Fermilab, where at that time, this proton and its antiparticle called the antiproton, they were colliding. So that's a Tevatron collider. It's about 4 miles of circumference is this big ring. But there are 9 different kinds of accelerator to make this one, so it's quite complex a system. Now I'm currently collaborating on an experiment called Atlas using Large Hadron Collider. That's a proton and proton collision, and the circumference is about 16 miles. So if you look at the tunnel here, it's cut off, then it looks like that. So this itself is this level of size, and you can imagine this is 16 miles long, and very, very advanced technologies used, an incredibly powerful machine. So I pretty much followed the more and more powerful accelerators because I needed better tools. So these are no longer running because they've done their work done. All this good juice, nice juice already used up. So they are running with a different kind of modern technology accelerators, different from this one. So there are still very active research going on in these laboratories and different facilities. What about the detector and experiment? So in Japan, I worked at the experiment called the Amy experiment, and that's my photo, and this is a part of the collaboration, and total about 60 physicists from 4 countries. And you can see that behind there's a size of detector. You can see what the level of scale of the detector. When I moved to a CDF experiment, and that's myself comparing to the scale of this detector, you can see how things change. Just from picture, you see more complex and bigger, and there are more people. We started with a few hundred people, collaborators at the beginning, but later on it doubled at the end of the experiment from 20 countries. Now, Atlas experiment, and here you see that the human being here, This person is, by the way, much taller than me, so you can also scale that up. And it's gigantic. And not just the size, but the complexity and this technology is quite advanced. So many ways, a very, very powerful experiments. It's about 3,000 collaborators from 40 countries. But there are many different kinds of detectors involved and different physics can be done. So it's not that everybody does exactly the same thing. Topics are much broader than others. So I want to mention that Yale group has a very strong contributions to both the CDF experiment and Atlas experiment. Sarah is, again, they have been doing great job and fantastic major contribution to this experiment now, and she was also worked at CDF experiment before. So again, here my journey has been better and more powerful detectors from beginning to now, and continue. So when I look at the detector, so collisions happen from one beam of particles to another in the center of detectors. And as I mentioned, these very interesting exotic particles decay immediately, ends up with all different particles coming out. So our detector's job is to really identify each of them, who they are, and what kind of properties they are. So for really trying to understand who they are, we want to know how these particles interact with the detectors. Just not one kind of device may not be able to tell all the story, so we have many layers of different technology. We want to check each particle, how they respond to each layer. So in some sense, they are also like onions with many layers. So when I describe detector to people, I often say, like imagine onion. So here's another onion analogy, and detector also like an onions. So I said that this is the picture when I started the research, and the 1995 CDF and D0 experiment discovered the top quark. This is the heaviest, the most massive particle ever seen. It's about 170 times of the proton mass. And in fact, if add up Z boson and W boson, this will become about top quark mass. And year 2000, there are tau, another kind of a neutrino, tau type neutrino was discovered at Fermilab. I was not involved in that experiment, but there was an experiment using the neutrino beams, and they discovered that. So one of the main big questions, as you may have heard from other talks and from other the information in news, that there was a big discovery happened in 2012. There was a discovery of a Higgs boson. So that is the particle responsible for giving masses to these particles. So one of the big questions to our field is that, yes, we measured the masses of these particles, but how do they get that? And so that's what Higgs can explain. That has been predicted for many decades. Finally, it was discovered in 2012. This is the pink, it's spin 0. This is a unit of integer spin, but that's we call boson. So it's not the exact same as the other ones, but still boson. Still, if I divide the boson versus fermions, still Europe just have discovered all the bosons. Interesting. So now, with all the properties of these elementary particles, whether masses or charge and spins and all that, we can build a theory. So that's the standard model of a particle physics. So that's the main theory, current theory in particle physics. So like what 19th century scientists have done, we also make a table based on their properties. So there are 6 quarks. These are a positive charged one and negatively charged one. And there's 3 types of charged leptons, like electrons, but with 2 more massive ones. And there are very interesting, fascinating, the neutral neutrinos. There are 3 of them. There are also anti-particles of this one, but I didn't put here. And there are force carriers for electromagnetic interactions to weak interactions or strong interactions shown here as well. So when I studied this wasn't there and this wasn't there, and this wasn't there. But the last couple of decades, these are all filled as sort of predicted by the standard model. So it has been very successful model, and almost all experimental results beautifully fit in this framework. So now the question will be then, will you stop here? Many people thought that particle physics is over since we discovered all the particles predicted by standard model. As you can imagine, of course we don't stop here. How could you, right? So that peeling continues, but it's not just because you just want to see inside more. It's much more than that, and I want to tell you why we felt that really peeling this further is necessary. So that is, there are many questions still unanswered by standard model of particle physics or this current theory. For example, there are 6 quarks, but who said that 6 is the right number? Could it be 4, could it be 8, but why? So that kind of why question cannot be answered. They have a charge of some certain value, and who ordered them? Who said that that value should be? Just so measuring just a charge or mass, we cannot be satisfied. We want to understand the reasons behind that. There are, if you look at their properties, this one set and another set and 3 sets, there is a very similarity. So we have 3 generations of 3 families, but again, why 3? There are 4 forces in the nature, and here standard model of particle physics describes 3 of them: electromagnetic force and weak force and strong force. But if you look at their behaviors at very high energy particle beams, electromagnetic forces and weak forces, they look the same at very high energy. So we already know that they are not 2 separate one, but that really come from one. If you look at strong forces, their behavior also getting similar and similar to the other 2 at very high energy, the regime. So in other words, we imagine that when universe is extremely high energy, high temperature at the beginning and small, tiny universe, there was only one force. And now as universe expanded and cooled down, now it become 4 forces, split into 4 forces. So that's sort of what we have in mind. So anyway, that's really true. All the forces become one or not. That's another big question. When we collide particle and particle, we produce a similar amount of particles and its antiparticles. So that means that at the beginning of universe, again, when universe is extremely high energy and high temperature, we imagine that very similar amount of matter particles and antiparticles there. But some reason the current universe is totally dominated by matter particles. So the question is what happened to those antimatter particles that must have existed at the beginning? So that's a big question we cannot answer. And if you look at the neutrino behaviors, they are very different from the others. And so there are very exciting, rich programs going on with the neutrino research. And again, so understanding their behaviors, why they are so different from others is one thing. But we also think that they might have some clue why the universe is dominated by matter and what happened to the antimatter's question. So these are kind of why questions. There are other questions. If you look at the rotating or spinning galaxies, this is, by the way, is due to gravitational force. But if you calculate the rotational speed based on visible object and visible matter, way off, very, very much smaller than what we measured. So that requires another kind of a matter, about 5 times more than our visible matter. But we haven't seen it, so that we call it dark matter. And there are very the active research going on there as well. Another question is that, as I said, the universe has been expanding, and most of us thought that now the expansion rate is kind of small and smaller, so slowed down or kind of stable. But about 2 decades ago, again, very surprising discoveries such that current universe is the expansion rate is accelerating. Again, this is a very surprising result. And when something is accelerating, that might be associated with the energy. Then we don't know what kind of energy, but that might be, and we call that dark energy. That means we have no clue. Or it could be we have a lack of understanding in gravity. Whatever that is, these are big questions. So if you think about the universe, what visible matter is only about to 5%. There's a huge, about 25% of us, dark matter, we don't know what they are. And dark energy, about 70% level, we have a less clue, and that's that. So things I talked about all, successful, we are talking about only 5% of the universe. So you realize that by knowing so much, you also realize that you don't know a lot about universe. So that reminds me thinking, the more you know, the more we know we don't know. Again, this wisdom has been there, and we just finally agreeing with that. So peeling another layer is we feel that we are getting close to see something, another breakthrough, at least answering some of those questions that I laid out. So we have to continue that. So that means it's not just peeling more, but the more we understand, the deeper we go, we'll have a more complete and more elegant theory so that those questions can be answered more naturally instead of just measuring and put by hands. So my journey, I mentioned about that, and we are working on the experiments at the Large Hadron Collider. This will continue another couple of decades, but any of these projects and facilities, very, very gigantic and complex, that means it takes a couple of decades to thinking about what kind of facilities are needed, whether we have a right technologies, most likely we don't, and we have to develop that technology and build. So this is several decades of project. Therefore, we have to think now. So we have a lot of activities going on, what might be the future ones. So I'm just talking about things that I directly involved. There are other parts of neutrinos or dark matter or dark energy. There are many other projects also similarly going on, but I'm just focusing on the collider that I'm involved in. So currently, Japan, none of these things I'm talking about is proven. This is still planning or this stage, and we don't know which one will be approved by their government or community yet. So Japan has a proposal to build about 25-mile long, so linear accelerator with electron beam and its anti-particle positron beam and having collision at the center. So it's the north part of Japan. China has ambition of making about 40 miles long circumference circular collider. They want to start with the electron-positron collisions. In the same tunnel, they want to add a proton-proton collider later. CERN in Geneva, this is the Large Hadron Collider currently operating and running 16 miles circumference. They have ambition of building about 50 miles going through all this Lake Geneva. That would complicate this construction of this project. But they have an ambition of building proton-proton collider, or it could be also electron-positron or electron-proton collisions, but that's in the plan. From US side, we have a bit different plan. Instead of going bigger one, it's trying different kinds. We never done before using muons. Muon particles are much more, about 200 times more massive than the electron. But this one is unstable, so there are a lot of challenges, and we don't know whether we can build it or not. But that has attractive the component, which is if you can make it work, we can make it small with a similar power of the performance. We can make it, we build even within Fermilab site. So again, this is a long way to go, but this at least some R&D or research and development going on. So we don't know which one will happen, but we have a lot of plan, and the research and the development of technology is going on for future projects. And these are all the global projects, so entire world, the community has to decide together, and we have to contribute to build as one facility. So I mentioned a number of times that the universe beginning and now, we are about 14 billion years old of the universe, and start with the small and expand it, and this is very cold, the universe. This is scale is not linear, so you'll see that 1 second is somewhere here, and this is 10 to the minus 10 seconds here, and 3 minutes and 14 billion. So we are thinkers, human beings, and we have been searching for elegant and more complete theory. So we can do that by just peeling layer one by layer one, as I mentioned, and this is our current stage of the building blocks. But they might be made of even something smaller. Wouldn't it be nice that even though there are 6 quarks and 6 leptons, but they are all made of something smaller, but just by one kind of element? They would be much more elegant, complete theory. It may happen, we don't know, so we'll continue. So this is a kind of peeling inward. But it's similarly really peeling inward, meaning we need the high energy, the tools, high energy beams. It's similar to we are going backward. So we are peeling backward in time because we are heading toward the higher and higher energy, or the conditions, which is a part of condition which is similar to a very early universe. So again, more powerful and higher energy accelerators will lead us to go even earlier time of the universe. Of course, these two are all connected. Things we discovered with the accelerators in this way and that way. I showed you about all the particles, new particles, and these particles or building blocks that make all of us. They are all together make this theory, and we are going after complete and elegant theory. So we'll continue to peel away at the more hidden layers of truth. And again, we believe that we'll find a more complete and elegant theory. But as is the case with the onion, we must wonder whether they will ever emerge an ultimate layer where the peeling must stop. Thank you.
Thank you so much, Young-Kee. We have a number of minutes for questions. I am the dance half of the Physics and Dance equation that has curated this series and co-teaches the course. Those who have been following the series, the students in our class, may feel like their heads are spinning. The last lecture we heard was on innovations in avant-garde dance. And here we are now with a beautiful explanation of research methods in particle physics. I want to take a stab at making a connection and comparison with hopefully a question at the end of it. With Yvonne Rainer, our previous dance artist guest, we had a clear image, Yvonne in a studio working alone, however, with the ghosts of dance history inhabiting the space. And what we have here are scientists still with that history working in relation to, but with 3,000 collaborators, for example, in the Atlas experiment. So very different research scenarios. However, I believe both disciplines are engaged in modeling movement and modeling space, finding ways to model motion and space in very different scales. And what we've bumped into in thinking about comparisons is this idea that art somehow invents and science somehow discovers, and that they're separate and they're different. What I want to ask here is, isn't the standard model something of an invention? It's an unpeeling of a reality of phenomena as you're observing it, but it had to be crafted and constructed. It's a way of modeling an understanding of mass, movement, space that helps you get to some kind of truth of natural phenomena. So these models seem to me to be something that get invented, perhaps more than discovered.
Well, it's, science is different from math in a sense that doesn't matter how elegantly formulated, if nature does not agree with that, we say no. So in that sense, it's really side by side. In some cases, the experiments sort of led first, and the formalism and theory come to explain that. Even that formulating the theory, many, at least the particle physicists or in general scientists' point of view is, if the theory looks complicated, then it's probably not good theory. So it's a beauty of how elegant the mathematics form. That actually really has a lot of value. So again, the history has told us that if the theory looks elegant, then more likely correct one. That doesn't mean just elegant one is all correct. Of course, you have to test against the measurement. So some cases, experiments discover something and followed by theory. Then some other cases, theory formed based on experiments, but theory has more than what's already observed, but something else can be predicted by the theory which explained this one, but something else. And then we go and look for that particles. So like standard model, many ways is studied by experiments. But then the standard model theory came about to explain that, and then realized that while my theory and our theory explains all the existing phenomena, but something else has to be there, like a top quark and bottom quark. Top quark has to be there, and Higgs, again, trying to understand or trying to make this whole theory that explains all the phenomena, we must have also Higgs boson there. So that, in that case, theory predicted it. So it really goes side by side. I would say not one is, another. For dance or art, other the art, there's no so-called some factual truth you can compare against. That's different from science. So in some way, art you can invent, and I guess audience has to judge whether this is a great art or not. That might be constrained, but it's different kind of constraints in forming theory. I don't know whether I answered
You're getting at it, and we'll keep talking about it. I have many more thoughts and questions, but I want to open the floor for others to jump in.
Hi, thank you very much. I wanted a little bit more of the natural history of these particles. Once we got that there were up and down quarks inside the neutron, inside the proton, different combinations, and then we go off and we understand chemistry, but then you said there's more, and all these leptons and all these exotic things, and the top quark, and the top quark's so massive it can't possibly be in the hydrogen. It's not sitting around.
Right.
And so where are those things in the world, and are they there just to help you confirm the theory, or do they have a role in the universe? Are they out there now? Are there Higgs bosons in this room? Which of those particles is represented in this room, and which of them are not? And sort of creations in order to confirm the theory. And do they have a role in the universe other than helping you know that your theory is right?
Yeah, so certainly, the fact, again, the experimental results came first. You discover things from experiments, even though they may not exist in nature now.
So which one of those do exist in nature now?
So most of electrons and up quark and down quark. There are also like gluons, which kind of binding quarks, and we need another particle like a W or Z bosons to understand the radioactive decay. So
you showed that the gluon was much more massive.
Well, gluon is massless. Sorry.
Pardon?
Gluon is massless. Gluon has a zero mass. I forgot to mention.
Oh, it's the
W and Z bosons are massless.
Oh, okay. So
right.
they were the big blue gluons.
Right.
In your map.
Gluons actually is separate because I should not.
So, but there aren't those bosons. A big massive boson is not sitting inside the hydrogen, right?
That's correct. But if you want to understand how radioactive materials decay, you have to have. Yes, it's not that you see things, but we need particles like that to explain how it decays. So we see the beginning and end radioactive materials. We don't really see the WM boson, which is the intermediate stage, but we need that to explain. And then, so that has to be, again, initial final states to understand that we need something like that. And that pops up in the collider. So that matches. So it's not that always you have to see it. It's, again, those ones will be also in the virtual stage, meaning that a lot of things we see, even you can think of any particle, there's a quantum fluctuation going on. And that fluctuation, of course, we don't see them, but those quantum fluctuation level, all these heavy particles have to be always created and disappear, created. That always happening to explain the properties. And we require those particles to explain things we see. And we believe that it must be very early universe as well, because high energy, high temperature, we can create them, and then early universe has that condition, therefore must be there. So that means that at the beginning, early stage of universe, they played a very significant role to make who we are, too, beyond the virtual stage that they are here.
I think in answer to Emily's question, if you have a Platonic view of the universe, you think that there are things, great things beyond what we see to be discovered, the ultimate pictures, models. I think that in science, theoretical high-energy physicists tend very much to like the idea of discovering the laws, the basic laws. But it's because they're Platonic in their philosophy. They think they are really getting down to something beyond what we see. Now there are scientists also who are very Aristotelian in their approach, who figure that we are sort of inventing things, that we're going like discovering some things, how they work. But there's no ultimate conception or Platonic model that we are discovering. I think it varies considerably with the field.
I think
and then in
that's
that sense,
good,
I would like to ask you a question about, from those two viewpoints. What is the information about dark energy and dark matter comes from
space. Yeah.
Space,
Yeah.
at big scale. What does it have to do with high energy particles, which are very small?
Right. So, for example,
But they're
dark
not
matter. We of course, we don't know who they are, but one great possibility is dark matter themselves are the building, meaning that the elementary particles. So, if that's the case, collider should be able to produce. So we have a lot of searches going on, dark matter searches, using the Large Hadron Collider because they have enough energy, and we may be able to produce dark matter particles. So that's kind of relationship with the particle physics.
Let me get the facts straight. Does our information about dark energy and dark matter come exclusively from astronomy?
That's true. That's true. The observation is there. So what we are trying to do is whether we can create dark matter from the accelerators, because there are a lot of theory about dark matter tells us that might be elementary particles. May be wrong, but at least that's how we connect.
Well, then I would like to ask you if putting together dark energy and dark matter and with the high energy particles that you are discussing, putting them together as part of the great energy description, isn't that a Platonic idea as to energy must be explained, and therefore it is the same thing. Energy is the same thing, and therefore it is just one subject that you are studying. And that's Platonic, isn't it? Because there may be no connection between
Yeah.
dark energy and the bosons.
Right, so we do.
Higgs bosons.
Yeah, I agree that we do believe that matter and energy, these are all related, and this is the one form, matter and energy is different forms of the.
That's not the question. That's thermodynamics. The question is, what does dark energy have to do with high energy particles, with particle physics?
So, for example, dark energy, again, the many theorists believe that it could be in the form of a scalar particle, scalar field. Then you could imagine, again, this is a stretching far, but Higgs is a scalar field. So this is the first scalar field particle that we ever seen. If dark energy is also in the form of scalar field, and there are two scalar fields that might be able to mix. So there might be some connection. I'm not claiming that is the right thing, but at least some the thinking that it can be mixed between the two. So there might be some relation. Although if you use Higgs field trying to calculate cosmological constant, that's way off, and I don't think anybody knows about that.
I like pursuing these two forms of philosophy to interpret continually what you're saying. And so isn't it possible that scale of fields is, again, a concept that you have from in different parts of the work, and to say that it would be universal is a conception that is certainly questionable.
Yeah, I can buy that. Okay. I can buy it. And you may ask, we come up with the current theory. Are there any, you start differently, would they come up with a different kind of theory, which is different from, and it's totally possible. As long as that explains what we have seen, that could be plausible that another theory that can explain. Again, I think we are going, you answered quite nicely to Emily's question. Our kind of role as scientists, we are not creating. There is, we are trying to discover what nature is telling us and how to explain the nature. So in that sense, invention and the discovery might be a sort of different concept. Again, we can talk more at the dinner. Yeah, interrelated.
So very, very interesting talk. Thank you.
Thank you.
Two things. First, just a comment on dark energy, speaking as an astronomer. I think the reason these things are discovered by astronomers is because we see their impact only on very, very large scales. And so observations in a terrestrial laboratory just don't reveal the effects of dark energy or dark matter yet, although you may find dark matter particles at the LHC. My question is more about, having been a physicist, I think, for even longer than you, I'm very familiar with the idea of elegant theories being preferred, simple theories being preferred. It's sort of, and probably since Occam's razor, it's been the preference, at least that long. But why? I mean, what is there about elegance or simplicity that is closer to correct than complexity? I mean, if we look in the biological sciences, for example, it's extraordinarily complex. In fact, I have a problem with biology because if they're, why is it so complicated? Why does this DNA code for that protein, code for some other protein, blah, 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 blah? Why don't you just make it the way you want it to be? I don't. So anyway, we have these sort of different philosophies of science. Right. Why do physicists believe elegance is somehow closer to nature, and how can we ever tell?
That's an interesting question. I mean, not even particle physics, but some other condensed matter physics side, if you look at, they all look for very vast, different phenomena, looking for universality. So one thing that explains all the different phenomena, that's kind of pursuing that. It's similar to what we are doing in the particle physics. I don't know. It started with even very ancient. Everything. It's a perfect sphere is more valued than others. So all those symmetries are another good example. We use a lot of symmetry principle to come up with theory and all that. That's again trying to see something. Symmetry means more elegant and simple. It gives us more insight. Might be, there are a lot of tracks historically. I mean, just looking at Newton's law, what's happening on Earth to what's happening in space, with the same laws, just explain both. That happened to be also correct, and just seems more kind of our experience and histories are probably so far showing us that looks that way always. So I guess based on hundreds of years of kind of track records, kind of guiding us, that might be the right direction. I cannot give you a better answer than that. But I guess in some sense also a notion or definition of what beauty is. It's interesting question. We like to have a more perfect, is more correct and more beautiful. It may or may not be, but that's how we have been pursuing with the whole humankind in some sense. Right now, of course, the symmetry is broken. So that creates a more, the rich phenomena. So that's where we are. Seems like the nature is not always well fit in symmetry. That's what the Higgs mechanism, and in fact, it's much more complicated than. Then we are looking for maybe something beyond that and simple, and we can explain all the complexity from the more elegant theory. Thank you.